Okay, welcome everybody. Now today, I'm going to talk more about the notes. With certain things happening, I forgot to put the notes I talked about the other day on Blackboard till this morning. About 5 this morning, I realized I hadn't done that. And so that's now on Blackboard. So those of you at home, if you want to go to Blackboard, you can look at the things from there. We can also put it up on the screen. For those of you here, if you didn't, anybody not have a copy from the other day? Okay, as long as, so that way people here can keep track. And so now I'm not trying to just go by pages, but essentially we're going to be around page 11, I think, to start with. What we talked about on Wednesday was what differentiability is and stuff. I'm going to restate that and make some comments. Looks like I can be seen. We might, by the way, be getting another, we're going to try maybe another thing to do in class. There's a device we might be able to get that will be closer to the board instead of what you have here when you're home. And also supposedly it follows me around if I move. So we'll see if that is something that will help us have a better class. Maybe replacing me be better, but that's not the next thing that I know of. Anyway, okay, what we have a function f, we have a function x naught, and now I want to sort of just put down what it is. If the function is vector valued, so what we're going to be doing here is going from some subset, let's say in n dimensional space, to someplace in m dimensional space. So that says if we wish to, that there are m, as in mother, m
Dr. Brady.
that are real valued, that make up the complicated vector valued function, okay? And
Dr. Brady.
O means that the limit of a difference quotient, and so it looks like what I'm writing so far a little bit like what you have for Calc 1 so far, except I can't divide by vectors, so I have to put a norm down here. We have a vector x and a vector x naught. Here I have an x and an x naught, and if I stopped there, that would look very much like a derivative that we had in Calc 1. The trouble with that is that limits are single valued. You get a number. Yes, sir?
We have someone that needs let in.
Somebody else wants to come in? That's good. Cameron wants to come in. Thank you. Well, come on, Cameron. Cameron is joining, but he's not here. Cameron is now here. Okay. All right. So if we had this, this would look very much like Calc 1. The trouble was in those days, this thing equaled a number. And the trouble is for vector valued functions, a single number does not do anything for us. So you can't have it equal to two numbers and things. I can have it equal to a vector, but it turns out that doesn't make much sense either for what we want to do. But in this particular case, the definition is that the function is differentiable if there is a linear transformation that you stick in here. And this is L of. This is like f of x. This is not a product. This is a function of. And if that, when you get done, equals 0. Now, this is the first time, as far as the board anyway, is concerned, where I've had vector valued functions and vectors all over the place, so everything's underlined. And this L is a function from all of n dimensions into m dimensions. Okay, so L is a linear function. That's the definition. If there's a linear function that makes this limit 0, then the function is said to be differentiable. Now, there's several things we do with that because linear functions have a special form. So because this function L is linear, so I'm going to put in parentheses here what this means or what we get from it. In this case, there is an M by N matrix, which I'm going to call A for the moment, such that L of X is the matrix A times X, where you write X as a column. It's matrix multiplication. Now, let's go down to one dimension to one dimension. A function that's linear from one dimension to one dimension looks like AX. That's a straight line that passes through the origin. When you graph it, if you set this equal to Y, you get a line, a non-vertical line. And differentiability actually is that idea. We could have defined differentiability by using a linear transformation instead of using a slope, because for every linear transformation there's a slope, and for every slope there's a linear transformation. So when you translate that back to one dimensions, you can get this over to the other side and it's just a number. Okay, if I'm going from n dimensions to one, several dimensions to one, in the notes I had a section where we did 2 dimensions to one, okay? Then the L of X is a vector A dot X, because now the X's are vectors, and linear transformations, no bar under the L because it's real valued. This is a real number when you dot product. This is what linear transformations look like from n dimensions to 1. If it's 2 dimensions to 1, this will give us a plane through the origin. Because if it's 2 dimensions, if n is 2, then what we get is something like Z is AB dot XY, which is Z equals AX plus BY. So in 2 dimensions, you get a plane through the origin, okay? In more dimensions, we have to call that something else. We call it a hyperplane. Anyway, so when we have the range being one-dimensional, we have real valued functions. This is a vector valued function. There are M of these functions that are real value. When I only have one of them, then we get lines and planes. Okay? Now, for each dimension you go into, you get something like this. When you put that together, that's a matrix. And the AX that I wrote down on the little left here, this is thinking of this as an M row, N column thing, A11 to A1N, because there's N columns, down to AM1 to AMN, times X1 to XN. We make the vector vertical to make it like a column so we can do matrix multiplication. If you multiply this matrix times this, I hope you know how to multiply matrices. If you don't, we're going to learn real quick here. What you do is you do the dot product of each row with this column. So if I wanted to write this out in one column, this would be the first row times and so on. And so I have a little trouble writing all that. So if we call the first row, so if I make this, the first row is A1 and the mth row is AM. Now this looks like a column, it's not. It's M wide, okay? Sorry, N wide and M deep. But if I try to call the first row by this name, the multiplication of this row, first row times this, is a dot product. And the second row would be the second one. and so on. And the mth row would be the mth thing. Basically, a m by n matrix can be thought of as m rows. And if I think of it that way, this becomes m dot products. Each dot product being a linear function that's real valued, you see. So this idea for one goes into each row of this because I have m of these things that look like this. You just have to get into this and think about it. It actually is nicely worked out. I don't mean that I'm not bragging about what I'm doing. I'm telling you, this is brilliant when people work this out. I'm just reporting it to you. Yes, sir.
So it's the dot product of all of the stuff in the row, what you're saying?
It's
Together with
each
the
row,
dot product?
when you mean each row is n numbers.
Yeah,
This is n deep.
yeah.
And when you do a dot, when you do A11 times x1 plus A22 times, sorry, A12 times x2, it's a dot product. Okay. So, and again, when you multiply an m by n matrix times an n by 1 matrix, you get an m by 1. You may remember that to the outside, when you multiply two matrices together, it's the outside numbers. It's the row of the first and the column of the second to give you the result. So when I do m by n and n by 1, that middle number has to match. I will get an m by 1. That's a column. Now, it looks like this because I've written vector functions in columns. But we can change this to a vector if we wanted to by just putting commas and writing it sideways. It's just with matrices, sideways and vertical make a difference. For vectors, whether we write it with commas in between or not, as long as we call it a vector, it doesn't matter how we write it. But for matrices, we have to be careful about the way we write stuff. That's why when a while ago, I said, technically, when you see me write this, it looks like a single column. It's not. This is meant to be symbolic of this. Each one of these is a vector. So this way of writing is abusive notation. This way of writing is more correct. But if I'm going to later change it to this is now correct. It's just, I shouldn't write this for that in a matrix. But notation becomes a problem with this stuff. Okay?
So you can
So-
technically not have a matrix that has vectors in it.
Well, the linear transformation for such functions is a matrix. So you're stuck with an m by m matrix. And we view it row by row maybe, but it's still in mass m by n. So if I have a function from 2 space to 10 space, it's going to turn out that you're going to have a 10 by 2 matrix of numbers, except they're evaluated functions. So sometimes we're going to write a bunch of functions in there. And what they're going to be for differentiability is partial derivatives. So if I have a domain of 2 dimensions and a range of 10 dimensions, the domain will have 2 variables. There will be 2 partial derivatives with respect to the first variable, with respect to the second variable, because it's the domain space that tells you how many variables you got, and that's the partial derivative, how many partial derivatives. But I'm going into 10 dimensions. So it turns out to be a 10 by 2 array of partial derivatives. Into each dimension you go, you have 2 partial derivatives. That turns out to be 20 partial derivatives. One for each of the real valued functions. Anyway, this will take a little bit of time to get used to, but once you get used to this, it makes it easy, all you guys. Okay, so this is the definition of differentiability. And instead of writing L, we call L something different. Okay, and I'm going to change that. I'm going to rewrite this definition I'm going to erase underneath because I don't have any space here, but this is all in the appropriate page of your notes that you now have available on Blackboard, or if you came to class, you have a copy of here. Instead of writing it this way, and if you allow me to, I'm only going to change this part right here. In other words, for my space, I want to write this whole thing every time. In other words, I want to replace this thing right here by something else. All right? And it's easy for me to do on the Blackboard. Once I get it, I can just put it there by erasing it and sticking the new one in there. Okay? What I'd like to have, and what I have on a page, is several of these things, one after the other, where you're replacing, but I'm not erasing the original one. But anyway, you can replace DL with the symbols df of x naught. So instead of L, the way we write this thing is this. And this has a name, well, it has several names. What I call it is a differential of f at x naught. And it is a function. It is a linear transformation. df of x naught is this L. It is this thing, this AX, depending on what dimensions I'm talking about. So this notation replaces that notation. And from my space, I hope you understand I'm going to replace it without rewriting this several times, because I just don't have the space in here that you guys can see. So instead of L, we're going to write DF. And that's a function. And it's strange because it looks like a product, but this is a function of. This is like f of x. You know, y equals f of x. This is df of x naught of x minus x naught. Now, I will write the alternate thing here with h. The other thing you can do with differentiation is write the difference quotient as x naught plus h minus f of x naught minus df of x naught. That's the name of this thing. These things all have bars. df of x naught acting on h. Again, it's a function of h divided by the norm of h. This is the alternate way of writing the thing. Now, but what is this linear transformation? It is, earlier we said L of x is AX. And so instead of df of x naught of this, I can write the matrix A times the vector x minus x naught. So what's going on here, I'm going to write it here. df of x naught, that's the function acting on x minus x naught, the value of the domain value, that equals some matrix A times x minus x naught. This is a matrix multiplication. So f of x, if this were like y equals f of x, a function of something is a matrix times something. I'm telling you what this is, sort of telling you. I haven't told you what A is yet. What is A? It's the matrix of partial derivatives. So what A is turns out to be the first function with respect to the first variable at x naught, the first function with respect to the second partial derivative at x naught, and there's n of these, n of them. You gotta be careful with getting all the right stuff said here. What you get in every row of this matrix is a bunch of partial derivatives. What I've just tried to write down is the first function f1. I use superscripts for that. Not a derivative, this is a number. The first function, the n partial derivatives with respect to the first variable, second variable, and so on. Now, when n is 2, the first variable is usually called x and the second variable is usually called y. And so what the book does is writes f sub x here and f sub y instead of 1 and 2. But if I've got 100 variables, I run out of x and y because there's only 26 letters in the English alphabet. And so we use subscripts 1, 2, 3 instead of x, y, whatever. Okay? When we're doing with 2 dimensions or 3, we usually say x and y or x, y, and z. Above that, we usually say 1, 2, 3, 4 or 1, 2, 3, 4, 5. Okay? Anyway, the last row of this would be the mth function at x naught to partial derivative of that function. And finally over here, we'd have the nth partial derivative of the mth function at x naught. This is what this thing is. So this limit thing here is actually, now, remember scalar multiplication. Scalar multiplication is a number times a vector. What I have here is 1 over. This 1 over, I mean, it looks like divide, but it's not. We write it this way because you're used to seeing this in calculus. Actually, this is a scalar multiple here. Instead of being in the denominator, it's a scalar multiple of a difference of vectors. This f of x is an m-dimensional vector. F of x naught is an m-dimensional vector. And this is a matrix product of an m by n matrix times the x naught 1 to x naught n. And so this thing here is actually also an m vector because it's this matrix times that thing. And so you have an numerator here, which is no longer a numerator. It's a vector minus a vector minus a vector. So enough of an attempt at explaining that kind of stuff. The idea here is, and I'll do one more thing, and that is, it is sometimes done by, instead of this kind of notation, people use, and I guess I got to write it bigger, instead of, let's say, f sub 1, people write a sort of a psychedelic d. If you use dy dx for derivative, straight d, fourth letter of the English alphabet, dy over dx, in partial derivatives, we write a curly d instead of a straight d. And so the 1 here might be x. I don't know what it is because it depends on how many dimensions we have. But if 1 is x, so if I said f sub x here instead of f sub 1, that would be the partial of f with respect to x. So sometimes instead of f sub 1 or f sub x, we write that partial symbol sort of like dy dx in Calc 1 that you might be used to. Now, there's also a problem with that. So if you remember from Calc 1, sometimes instead of the prime, we use dy dx for derivative. But I think you've also seen df dx for derivative. So sometimes we put in the numerator the y, and sometimes you'll see people put in the numerator the f. You should have seen both of these notations for derivative. Well, we do the same thing here. If I name my variables, now I've got m and n, and m might be 100 and n might be 10,000, so I might have 1,000,000 variables or something. Okay? So trying to name them can get bad just in itself. But if it's 2-dimensional or 3-dimensional, so we can say x, y, z and stuff, then what you will see is things like dz by dx. And what does that say? Without knowing anything about how many variables and stuff, it looks to me like somebody's trying to say differentiate the third thing with respect to the first variable. That's what this looks like to me. Now it's only if x, y, z makes z the third thing. okay? And in this case, the z is in the range world and the x is in the domain world. That's always been the way it is, but you probably haven't thought about it. Because when you do calculus of one variable, you're going from x to y. F of x is y, x is the domain, and y is the range. So the numerator is the range variable, and the denominator is the domain variable. So it would be assuming here, if I have a z in the range, it would be at least 3 variables in the range, and the first variable in the domain is x. So I don't know if everybody's gone to sleep, or well, the people here all have their eyes open, that's all I can tell. They may be frowning, but they have their eyes open, mostly. Okay, so some of this that I've been talking about is hidden in the notes. And so if you look on like page 27, you're going to find the kind of stuff I just talked about, okay? And 28, okay? And so that, what I've been talking about is basically notation for what we want to say without telling you much else about it. Now, what comes prior to page 27 is stuff where you have derivatives of functions of one variable. So what does that do for everything I've been saying up here? Instead of having m functions, you only have one function. So instead of having a matrix, you just have a dot product here between two vectors. That the vector is a vector of partial derivatives, but it's just one row of them because we don't have m rows of them anymore. So what you get in the pages before 27 is differentiation with respect to one variable. One real valued function of n variables, okay, from n dimensions to 1. So that's what's on page 26 and 25 and 24 and so on. So if I go look at some of those pages, now for those of you at home who haven't yet done the Blackboard, let me find that. It'll take me a second to do that. I didn't have time to do it ahead of time. And I'll get it for us real quickly, I hope. But, okay, I'm getting there. Right. Okay, that's what I need to display. And we need to get a share screen so you don't see me anymore, which is a good thing. And share this. Okay, so now I have what's on the screen of what we have been talking about. And so I'm going to go up to, somewhere around page 23. And that's what I'm showing the people at home right now can see what's on page 23. And for example, what is there is what is the derivative. Now, it's not a derivative anymore, but we sometimes say that just because we're used to saying it in Calc 1. When I have products of functions that are real valued, okay, how do you define the product of two real valued functions? You multiply their values. So fg of x is f of x, g of x. Now, if we're in Calc 1 and you have the product of two functions, what's the product rule? You differentiate the first function, leave the second function alone, multiply to it, plus leave the first function alone, differentiate the second function, multiply to it, add the two things up. Okay? On page 23, proposition there, 1424, it's exactly the same, but the name looks different. So what you have on the screen, and I'm going to try to point it out with a sort of moving my cursor around. Okay, this DH, H is I'm writing as instead of F times G, I'm writing H as the product. So D times H or D times FG is, okay, well, differentiate the first function, leave the second one alone, plus leave the first one alone, differentiate the second. It's exactly the same idea, except now, what is this df thing and what is this dg thing? Okay, well, the df thing is a vector of partial derivatives, and the dg thing is a vector of partial derivatives. Okay, so you have a similar product rule to what we did in Calc 1, except now this differential thing, okay, except if you look at the video later, when you get to that part I just said, and you haven't got to the part now I'm going to say, so I'll say it, what I just said is wrong. Okay? Because these are functions, but they're not evaluated. Some of them are and some of them aren't. So let me show you. I'm going to get off this. I'm going to write on the screen and then I'm going to get off the share screen and try to show you that we have to interpret that. What I said is like what I want it to be, but it wasn't really accurate. So what I wrote is dH. Here I'm going to write dfg at x naught. What I wrote is g of x naught times df of x naught, and I'll show you all you guys here in a second, plus f of x naught times dg of x naught. This is what is on the middle of the screen on page 23 for you at home, and I'm going to get off that now so you'll see the screen here. This is, I just tried to repeat what was there, except in the book, or not the book, the notes, this is h. Okay? So it says dH of x naught. Now, what I said is, it's the first thing times the derivative of the second thing. That's kind of what I said. So if you go back and listen to the video, that's what you'll hear. And then 2 minutes later, you'll hear me doing what I'm doing now. Okay? Because this is a function, not the value of a function. And this is a function. And this is a function. So let's go back to Calc 1 for a second and talk about the derivative of fg at x naught. There you learned that it was f prime of x naught, g of x naught, plus g prime of x naught, f of x naught. And so in order to make it exactly the same, let me rewrite that second as f of x naught, g prime of x naught. This is the product rule in Calculus 1. Now, this derivative at x naught, that's a number, it's a slope. This is a number, this is a number, f of x naught is a number, and g prime of x naught is a number. You have the product of numbers added up as you can get a number. Fine. Now, but this is a function. So to make this one up here look like this one down here, okay, you evaluate the function at some place, like x. Okay, now I should have put bars under here. I wrote this quickly a while ago. But if I evaluate this function at x, then I look over here and say, okay, this is a number times a function of x plus another number times a function of x. Now I've made this look like this. Except in the original idea with Calc 1, f and g were functions. In this new idea, df and dg of x naught are functions. So when I write it without any x's and stuff, I'm writing it, now I can do it here. In Calc 1, I could have said fg prime equals f prime g plus f g prime. This is writing the product rule without variables. All right? And this is now writing the product rule with variables because I stuck the x in the appropriate places. Yes, sir.
So is the only way to tell that the basically like the D of a function also needs another domain in order to be.
Well, the df of x naught or g is always going to be a function.
Okay.
When you see that df of something, if you just see df alone, that's something else. We'll get to that. But the note right now, df of x naught is just a notation. It's not to be interpreted as anything except the name for the linear transformation. Okay, so you don't bother it. You don't detach the x naught away from the other part.
Yeah,
We will be detaching it, but not yet. Right now, it's just a notation. Okay, this is why it can be confusing. So when you see what I wrote on that page 23 or whatever it was that you guys can, we had at home a minute ago, the function, it was a functional thing, not a function evaluated thing. And you're used to seeing functions evaluated. Okay,
Dr. Brady.
I'll go back to that share screen. Hello, share screen. There's people chatting and I can't take time to worry about that right now. Okay, so when you see this here, the dh of x naught, so you who are in present today, I'm talking about the middle of page 23, okay? Above the words and the associate gradient vector, above that. Now, what's below that? Well, now we got something else here. Okay, so you and I have not yet defined the thing I now have the arrow pointed out, which is a triangle with an H on it. So we need to talk about that. Because we need to have better notation than what I've given you so far. Because, now, I'm going to get off the screen, the share screen again. I just wish you all were here and we didn't have to do all this. But, and I see it's, what, 10 after or 18 after? 10, okay. So I'm up here, I can't tell the difference. I was hoping it's not 18 from my standpoint because I got more to say. Anyway, when I have a real valued function, on page 23, these things are real valued. So the function f goes from some subset of n dimensions into the real numbers. So we're doing some subset into the real numbers, which I'm calling E1, but that's the real numbers. Now, so df of x naught, that's a function from all of En into E1, it turns out. And this is the name for the linear transformation when f is differentiable at x naught. So in here I got to put f is differentiable. I won't write all that out at x naught. That's what gives me this thing. Okay, and we said df of x naught, if I run into that like we did a minute ago, acting on x, okay, is now this is a real valued function of x. X is in n dimensions. F, or not f, but this thing of x, when I have a function from n dimensions to 1, and I take something in that world, that something of it is something in this world. So this is a real number. What real number is it? Well, earlier I said it was a dot x, if you remember. But then we said, well, what that really is the partial derivatives. I only have one function now, so there's no superscripts. I have the first partial at x naught, the second partial with respect to the second variable at x naught, and so on. The partial with respect to the nth variable at x naught, dot x. So now I've written out what this a is. It's the partial derivatives. So what I have is n numbers here, all partial derivatives. Now, by the way, we're going to be doing lots of examples as soon as I get all this notational stuff fixed up. Okay? So, what we need to have a name for this vector. You don't want to call it A. A doesn't tell us anything. I mean, it just says it's a vector, but it doesn't tell us what. This tells us exactly what. I have n partial derivatives. I evaluate each of them at x naught. I get n numbers. That's the ones I want. All right. This vector is called the gradient, okay, the gradient of f at x naught. That's its name. Now, we have two symbols for that at least. One is to use the letters GRAD, or gradient. And you will see that some places. Gradient is grad in terms of what it looks like, okay? Or we use an upside down, if you like, a triangle with a base at the top, okay? We write this. And this is called del, D-E-L. And when you read that, you say del F, D-E-L-F. The first three letters of the fourth letter of the Greek alphabet, if you like. Not delta, but del. Again, the inventors of calculus only had variables and they had to make names. And if you want to use delta, that's fine. I want to do something else, they call it del. Okay? So this is called del F of x naught. It's the gradient. What is it? It's the matrix of partial derivatives. So that allows us, when we do the original f of x naught, f of x minus f of x naught, remember we had it earlier, when we had an L of x minus x naught, that allows us instead to write the gradient of f of x naught dot x minus x naught. And if you have that in your limit for differentiation, you have that, this thing is now a number. It's a dot product of the partial derivatives with the x minus x naught. So this is another way you will see us write differentiation. Now, okay, and remember what we have here, if I write it all out, this is x minus x naught in the denominator and equals 0. This is differentiability. So if I have a function of n variables into one variable, into one variable, if I have from n dimensions to 1, and you say differentiability at some place, that means there will be a matrix of partial derivatives, which if I stick them in this formula and take a limit, I will get 0. Now, and for the moment, when you prove something, that's what you have to prove. So when I prove on page 23 that the product rule works, I have to do that kind of thing. I have to take the limit of this thing and make sure it equals 0. Because at the beginning, we have to go by the definition. So going back to the share screen now, on page 23 and so on, what you will see below the 1424 is the word proof. And the proof is an epsilon delta proof. Why? Because we're proving a limit. Proving limits requires you to do epsilons and deltas. So we are back to doing epsilons and deltas, and you'll see it takes a page and a half to verify. Okay? But all I'm trying to do is prove forever that this limit exists and equals 0. Now, that's page 23. What's before that? Well, there's a couple of interesting things before that that turn out to be very important, and I'm not going to have time to talk about them all today. But if I go back a little ways here, we're talking about sufficient conditions for differentiability. Before that, a very important one there on page, I'm going back, sorry if I'm making you dizzy at home. Okay, on page 14, we have what's called the mean value theorem for functions of several variables. Okay, now you may or may not remember the mean value theorem from Calc 1, but I hope you do, because it really is the fundamental theorem of calculus. It's not called the fundamental theorem of calculus, but you get the fundamental theorem of calculus from it. And it turns out to be why the fundamental theorem of calculus works. And so some people today would rather call it the fundamental theorem of calculus than what we normally call the fundamental theorem of calculus. So it turns out, whatever you want to call it, it's a very important theorem in Calc 1. Okay? You may remember it says that between 2 points on a graph, you draw a secant line, and somewhere in between there'll be a slope of the function that equals that. And you might have to recall that. Anyway, on page 14 of these notes, we have a mean value theorem for these kind of new functions, functions of n variables. And it turns out that that's very important. In the middle of that page, we have the tangent hyperplane to a graph. And all that is right now for people at home, I'm sort of waving a cursor back and forth. This part I'm waving back and forth is what is on my blackboard right now that you can't see anymore. It's the part f of x minus, and then what you see here in the middle, when I have xn plus 1, it turns out this is the equation of the tangent plane. And it's part of the numerator of that limit we had a minute ago. All right, now, if I go a little further down here, what do you do with differentiation things sometimes? And we'll do more of it. We calculate with differentials. And so it turns out, I gave you an example of that. We'll talk about that like Monday. Then, again, I don't have time to talk about it today because it's 20 minutes after. But what is at the bottom of page 15 is a trick for differentiating partial derivatives. Now, if you look for a minute at this function, at the bottom, it's 4 lines, 5 lines from the bottom of page 15, you will see a very complicated thing here. If you differentiate with respect to x, partial derivatives, that's still a mess. If you differentiate with respect to y, it's still a mess. This function is 2 variables, it's real valued, it has 2 partial derivatives, but each of them would be a bad thing to calculate. It turns out there's a trick for doing it. All you really have to do is calculate something like t to the 3/2. Well, there's a trick there. So you want to study that one. And then on page 16, we want to talk about when partial derivatives are equal. Because when I have things that have like m functions that go from n dimensions to m dimensions, like if that's from 10 dimensions to 10, I'm going to have 100 partial derivatives. I don't want to calculate 100 partial derivatives. It turns out that most of the time you only have to calculate about 60 of the 100. I don't want to calculate 60 either, but calculating 60 is better than calculating 100. Okay? And if this was 1,000, you'd only have to calculate about 500 or 600. And so it cuts your work not quite in half, but it cuts your work into like 55%. And that turns out to be a valuable thing if you're trying to do it all. Anyway, I want you to study these pages like 14, 15, 16, and so on. I've already told you what's up on 23 and 24. Okay? But once you look at those, and we're out of time here, and I'm going to stop the share screen and also stop the recording.